By 2025, global energy policies intend to push commercial fuel supplies from standard 10% ethanol blends up to 20 or even 30. Because ethanol carries its own oxygen molecule, pure ethanol requires far less ambient air, dropping the optimal ratio to 9:1. Introducing an E30 blend creates two distinct vectors of evaluation for legacy vehicles: static material degradation and dynamic performance parity. If the higher alcohol concentration dissolves the physical fuel lines or outsmarts the engine control module, the infrastructure fails. The first vector is physical integrity. Exposing legacy metal alloys and polymer seals to concentrated alcohol introduces the risk of galvanic corrosion and chemical plasticization. To measure this, researchers isolated the specific materials used in legacy fuel systems and subjected them to continuous immersion tests based on strict SAE standards, checking E20 against a standard commercial gasoline. The corrosion rates calculated for traditional metals like steel alloys, copper, and brass proved mathematically insignificant. The hardware itself remained completely intact. As this table shows, polymer degradation is highly material dependent. Elastomers like polychloroprene, SBR, and HNBR maintain nominal performance, but components made of NBR PVC, epichlorohydrin, and PA66 suffer severe volume swelling and a sharp loss of tensile strength. Material failure from high ethanol blends is highly predictable and structurally isolated. By retrofitting those few specific vulnerable polymers, the physical system is secured. The second vector is thermodynamic control. E30 drops the optimal combustion ratio to roughly 13:1. When a legacy engine expects standard gas but receives E30, it initially runs lean, processing too much air and not enough fuel. The engine control module solves this through a continuous closed-loop logic. The O2 sensor detects the lean exhaust and signals the computer. The computer instantly increases the long-term fuel trim, the LTFT, instructing the injectors to increase fuel output. Tracking telemetry from 50 vehicles, the red distributions show E30 forces a 3.5% upward shift in long-term fuel trim versus standard E15. On the right, the blue oxygen sensor outputs are mathematically identical. The computer successfully neutralizes the excess oxygen. This box plot tracks engine coolant temperatures. Operating on E30 causes an average increase of just 2 degrees Fahrenheit. At roughly 197 degrees, it sits safely below the standard 240-degree warning threshold. Most manufacturers code fuel system fault limits at 20 to 25%. The E30 oxygen density only forces a 3.5% adjustment. The legacy computer absorbs the chemical variance entirely on its own. The engine survives, and the computer balances the oxygen limit. But adjusting fuel trim doesn't guarantee the engine maintains transient volumetric efficiency under heavy acceleration. Engineers track true performance using absolute load, a continuous calculation of how efficiently the engine moves air and generates power under changing throttle positions. Evaluating absolute load requires filtering out chaotic real-world variables, like weather and specific driving habits. Researchers deployed a machine learning framework called Sparse Identification of Nonlinear Dynamics, or SINDI, to isolate the fuel's exact impact. SINDI mathematically stripped the noise from 16 different vehicle telemetry parameters. It determined that exactly 9 non-zero variables actually dictate absolute load. When mapped side by side, the governing coefficients for E15 and E30 align almost perfectly. The core mathematical equations governing how the vehicle generates power do not structurally change when ethanol concentrations hit 30. To eliminate any pre-normalization bias introduced by the SINDI algorithm, researchers required a second validation layer, a deep neural network structured with a single hidden processing layer. The neural network was trained exclusively on E15 baseline data, then blindly fed unseen E30 telemetry to predict absolute load. Looking at the E30 scatter plot on the right, the tight clustering maps to a 0.98 correlation value. The network accurately predicted the high ethanol performance. From the strict perspective of engine load and transient performance, the neural network confirms the two fuels are mathematically indistinguishable. There is an inescapable physical reality to ethanol. A single gallon contains roughly 30% less total energy than a gallon of pure gasoline. Burning an E30 blend inherently drops the vehicle's fuel economy. 1 year of driving data confirms a mileage penalty. E30 lost exactly 0.64 miles per gallon compared to E15. But tracking cost per mile, because wholesale ethanol is cheaper, the cost curves overlap and invert, offsetting the efficiency loss. If the market prices an E30 blend a minimum of 2.5% lower than standard gasoline, the engineering penalty of lost mileage is completely negated for the driver. The legacy engines survive, the computers adapt, and the economics balance out. Consider the systemic effect if just 10% of the existing non-flex U.S. fleet transitioned from E10 to an E30 blend. This chart models the environmental output of that partial transition. Utilizing the denser biofuel yields an average reduction of 34 megatons of emitted carbon dioxide year over year. Leveraging the inherent computational adaptability of existing engine blocks allows governments to execute a massive carbon reduction strategy immediately, without waiting decades to replace the global vehicle fleet.